what's up everyone? Welcome back. Yeah, sorry for the delay. This video is coming out a bit late, but I'm filming this in the Harnwell Lounge. It's pretty late at night, so that's the dedication we got going on here. We are going to, now we talked about the DFT, we did some examples. Now we're going to talk about, okay, the inverse DFT. Because remember, real quick, if this doesn't make sense, go back and watch the other videos. But the goal with the DFT is to take a signal and turn it into, like, take the signal and point out its frequency, right? Well, we need a way to go back, right? So to go from this way, we take the DFT, and then we want a way that, okay, like let's say I gave you this signal in frequency, can you take the inverse DFT to bring me back to what my signal was in time? So let's define the inverse DFT. If you remember, let's just recall, so let's do here in blue, recall that the DFT of little x of n is big X of k, and we say big X of k is the sum, 1 over root n times the sum from n equals 0 to big N minus 1 of x of n e to the minus j 2 pi k n over n. Many different interpretations of this. This is like an inner product between x and every single complex exponential, or x between, going across all the k's here takes the inner product of x with all of these different complex exponentials. If that doesn't make sense, watch the video before. Now let's talk about the inverse DFT. So remember, going from x of n to big X of k, that's with the DFT. And to go backwards, we use the inverse DFT. So the inverse DFT of big X of k is, let's call it x of n again. So what we're saying is that x of n, we can get back our signal in time by taking the inverse DFT of x of k, which means we do 1 over root n sum now from k equals 0 to big N minus 1 of x of k e to the positive j 2 pi k n over n. So two differences here to notice between these two. The first one is that here we sum over n and here we sum over k. The other thing to notice is that here we have e to the minus j, here we just have e to the plus j. There's no minus sign. Okay? So this says that if I have a signal x of n, I can take its DFT and get x of k, big X of k. Then I can take big X of k, put it through this system here, and get back my signal x of n. Very powerful, going to be very useful for us. Okay, so in other words, this line in mathematical terms, the inverse DFT is defined as f inverse of x of k equals x of n. That's what we're saying, right? And the other thing we set up here was that the DFT of x of n is x of k, big X of k. So I can replace this guy with the DFT of x of n. So in other words, what we're saying is that the inverse Fourier transform of the Fourier transform of a signal is the signal itself. That's the identity that we get with this IDFT. Okay, a lot of yapping, not much crazy there. Just remember this definition and what it looks like because it will be helpful. In some other time, we will prove this. It's not too bad of a proof. Just write out the sums. You have to flip the sums, interchange them. You're gonna end up, you're gonna flip the sums, and then something nice will happen. And you'll notice that you prove that if you take the DFT and the inverse DFT, you get the signal back. But we're not gonna do that now, in the sake of time. Okay, so here's the inverse DFT. Great. Now, there's two reasons this inverse DFT is useful. The first reason is that it allows us, right, to take our signal in frequency and represent it back in time, which is important, right? Based on what you saw in the intuition video for Fourier transforms, we want to go into the frequency domain, but at the end of the day, we also want to go back into the time domain. So that's useful for that. The other thing to notice is, let's take this guy right here. Okay, so let me rewrite it one more time so we can get it locked in. X of n is the sum from 1 over root n, k equals 0 to n minus 1, x of k, e to the j 2 pi k n over n. Okay, now let's actually, over here I'm going to write x of n, and here I'm going to take this sum and I'm going to expand it out. Okay, so let's, for the sake of this, drop the 1 over root n. It's just a scaling factor. It's not that important. We could have been in a whole new world where this 1 over root n was not here. Doesn't matter, just the way we define it. Okay, now let's see what's going on here. So let's choose k. Remember, this sum says go from k equals 0 to n minus 1. Let's go for k equals 0 first. So we plug in 0. We get x of 0 e to the j 2 pi 0 n over n. Okay, next let's plug in 1. So it's a sum, right? So then we plug in 1, x of 1 e to the j 2 pi 1 n over n. Okay, next x of 2 e to the j 2 pi 2 n over n, and so on and so forth, all the way up until n minus 1. So take a sec, pause the video, and think about what I'm saying in this line right here. What I'm saying is that my signal, my original signal, can be represented as a sum of what? Well, what are these? This guy right here is literally ekn, but e0n. No, this is a complex exponential of frequency 0. Recall that ekn is e to the j 2 pi kn over n. So here we just plugged in 0. Okay, great. This guy is e0n. Well, what is this guy? Similarly, this is e1n. This guy is e2n. And what am I multiplying each of them by? I'm multiplying them by their DFT coefficients. Remember, if there's one thing you remember, it should be that what does x of 0 tell you? It tells you how much of my original signal, how much of my original signal is related to this 0 frequency. Right? That's from the DFT video. So go back and watch that video if that doesn't make sense. But if that was clear, then this should be great. This is saying that my original signal right here, my x of n, right, can be represented as a sum of a bunch of these different frequency signals, all weighted by some constants, right? And these constants are exactly, what do these constants mean? Well, we know from before that this constant means how much of a weight does a frequency of 2 have in my original signal. And that makes sense, right? Because that's what we're multiplying by a frequency of 2. So everything is coming full circle, right? In picture format, what we're saying here is that let's say x of n, my signal in time can be any periodic signal, technically. So I can have like a square wave going on here, okay? What this is saying is that I can somehow say that my square wave is equal, so what would this frequency of 0? Well, that's a constant pulse, okay? Plus frequency of 1, okay, that looks like maybe this, okay? Plus, okay, so this frequency 2 is a little bit faster, okay? But what it's saying is that as long as I like take each of these frequencies, scale them by the proper value, and then add them together, right? I'll add a bunch of these frequencies, I can make up my original signal. It's a very powerful, result. It's saying that any periodic signal can be represented as a sum of simple sinusoidal oscillations, right? So for a little bit of a more detailed drawing, there's very good visuals. Just look up visuals online. But if we were to like expand this thing and like look at what the square wave might look like, it might look something like this. If we, take enough frequencies, we might get like this blue signal is a mix, right? It's a mix of some, high frequencies here, some low frequencies like that give you this sort of shape. So you add them properly, and if you do enough of them, you'll get exactly this square wave back. Okay, very cool. This is what we usually you might hear this as Fourier Series. Fourier Series. But in my opinion, this is the best way of learning it because it's very intuitive. As soon as you understand what the inverse DFT is, right? The inverse DFT, the Fourier series literally pops out of the definition. It's right here. You just expand the sum and boom, you get your Fourier series. So very good. We have covered that. We're gonna go on to the. Oh, please tell me. Oh, I'm recording. We're going to go on to the next video where we're going to talk a bit about modulation, and then we're going to be done with this unit, and then we're going to go on to continuous time signals. Okay, wonderful. See you next time. Thank you very much for watching.